Hello, everybody. This is episode 20. Along with us, we have Mark Nadal. He's going to present us GunDB. Mark, can you please introduce yourself?
Yeah. Hello, everyone. Thanks for having me on the show. I'm Mark Nadal, as you said, and I run Gun. I'm just going to switch right over to screen share the entire screen. So we're going to be covering a couple things today. Well, first off, reading the source code. But before we go into that, I'm going to cover some performance tips, and this is applicable to pretty much anything. We're going to quickly go over a data structure for what Gun does, and I'll explain that in a moment. And then we're actually just going to pull in the latest bleeding edge of Gun and read through the source code. So really quickly about Gun itself, to hit the developer website, you can go to gun.js.org, or if you want to go to the enterprise website, go to gundb.io. The simplest way to explain us is that we are an open source Firebase. So it's a database that's entirely written in JavaScript that focuses on real-time updates. And that sounds a little scary to have a database written in JavaScript, but hopefully the comparison to Firebase helps out with that. We raised a seed round out in Silicon Valley, and now we get to work on open source full time, which is pretty exciting. So I now want to jump into, that's just a quick summary. I'll be explaining more things as we go into it, but the point of this talk is to try and get to code. So you guys can see my screen all right? Good, okay. So first off, we've developed a new testing and development methodology that we're calling PTSD, Performance Testing Speed Development. And the reason why it has such a scary name is because the point of it is to take our machines and literally run a ton of tests on it with hundreds of thousands or millions of operations to just figure out how is the browser, the V8 engine, or other browsers like Firefox reacting to your code. Because JavaScript is very easy to have some snags that you write that become slow. So the first thing I want to focus on is this PTSD development methodology. So if you guys can hit db.marknadal.com/ptsd/ptsd.html, we're going to go over some of those quirks, okay? So let me just refresh this really quickly. We're going to start with doing absolutely nothing in JavaScript. And I'm going to run it, okay? And doing absolutely nothing in JavaScript allows us to only do about 250 million ops a second. That's pretty depressing. I have an entire talk on this, but I'm just going to skip past most of these things and jump down to things like for loops, okay? So we have a bunch of different ways that we could write a for loop. We could write a normal for loop where we say var I equals 0, I is less than list.length, I+++. And we could cache those variables where we set the variables on the outside and we use that, or we could use this handy, nifty for each with a callback. But you need to know the consequences of these things. Now, I'm not promoting micro optimizations of code because oftentimes readability of code can be more important. But when you're writing something as low level as a database, even though it's in JavaScript, you wind up having to pay attention to these sorts of things. So this for loop gets about 9 million ops a second. So you should take a guess. Is this one going to be faster or slower? Well, let's run it. It's already looking like it's going to be faster. So there's just a few little things that we can do to kind of optimize our code if we're shooting for such low-level stuff. And this little calculator right here will calculate the speed difference between these things. So that's about a 1 1/3 difference. But what if we want our code to be easier to maintain by using a for each function rather than having to remember how to, the endpoints of the array and stuff like that? Well, let's run it. Ouch, okay? So Chrome, and the story's a little bit different in Firefox, but I haven't tested it lately, is wildly different. You're only getting about almost 4 million ops a second with using a for loop. So if we calculate that, you can easily get almost 3.5 towards 4 times the speed performance, okay? And the reason why is this winds up boiling down to function calls in JavaScript, and this is pretty depressing. So I'm going to skip down to this. Functions are actually very, very expensive in JavaScript. So if we run one function, which isn't really doing anything. We get about 50 million ops a second, which is depressing. Firefox is way, way better at this sort of stuff. And actually, the latest Chrome Canary is improving the performance quite significantly, about doubling it from our experience. But if I call 2 functions, I'm getting almost half the speed, okay? Now, the story isn't that depressing because it's kind of, I think, logarithmic, where if I run 3 functions, it's not quite half the previous one. But the point here is that calling functions, even when the functions are already declared in advance, named functions, you're still getting like terrible reduction of performance just calling a function. There's all sorts of other little nuances, but the moral of the story is that if you then have an anonymous function, like we do with this for each, it takes even more of a performance cut because it has to create the scope every single time for that function as well as calling it. So we're going to be diving into code pretty soon, and we're taking this development methodology where we focus on just trying to squeeze as much raw performance out of JavaScript that we can. And I think you'll see it with some pretty incredible results. So before we do that, in order for it to make any sense, what the code's going to do, I first need to talk about the data structure that Gun stores things in. And Gun is a graph database, and the sweet thing with graph databases is that you can do key value, you can do relational, you can do document, or you can do graphs themselves. It turns out that any table can be represented as a matrix in mathematics, and any document is represented as a tree in mathematics. Well, any matrix and any tree can also be represented as a graph. So a graph is a superstructure of these other forms, but not all graphs can be represented as a table or as a tree or document. So if you hit up this wiki page, Gun's data format, we're starting with JSON just because it's simple for a lot of people. And if we take a regular object like this, just age 23, hacker true, name Mark Nadal, is a little out of date. I'm not that young. Gun has to append a couple pieces of metadata to it. So it looks more like this. It winds up creating a universal unique identifier for the object. And it winds up attaching some metadata because Gun deals with real-time updates as well as offline updates. There's lots of concurrency problems, so we have to track version numbers, but we do a little bit more than version numbers. It's actually a combination of, oh boy, it's a combination of vector clocks, timestamps, and lexical sorting. So it's a hybrid approach, which we found as being optimal for the base case, then you can expand it out to other things. But we're not going to talk about that in this podcast. But what if you have a document that looks something like this? So we have my age, we have that I'm a hacker, my name, and then we have a document, another object inside of that, that's also a hacker, and this is his name. Well, what Gun does, because it's a graph database, is it actually normalizes all the data into nodes in a graph. So the way that Gun stores this data looks more like this, okay? We take the original reference to my friend, and we just create a pointer that points to the universal unique identifier in the graph. And this way, Gun can actually be a lot faster because it only has to load partials of the data, and it only has to load the document when you request the document. So that's just a quick kind of summary of how the data is stored in Gun, because we're now going to jump into the source code. Well, I'm going to show you the code that we're going to run that we then look at. And it's necessary to know how the data is stored, so that way you understand as we follow along how the code works, what we're actually grabbing from local storage and from the server and stuff like that. So before doing that, you guys all need to clone the bleeding edge of Gun. Make sure you clone the 0.5 version of Gun. So clone git clone-b 0.5, github.com/amark/gun, or you, of course, can follow along with the podcast itself. Don't clone the current master stable, because that we're rewriting the entire thing for these performance metrics. The previous one doesn't have the same sort of performance. So let's jump over to our fancy code editor. I'm going to show you the actual code we're going to be running. So first, we wind up saving some data into Gun. So in this case, I'm just very quickly saving into the user's quote table, or however you want to think about the user's collection. A user that has an index of 1, and you can name it whatever you want, and they have a property called where, which is where they're at, and that happens to have GPS coordinates like long, lat, and in this case, I'm just randomly generating it. We're not going to be going over how we put data in Gun, primarily just how we read it out. And then we're going to perform a read such that we say, hey, Gun, get users, path into the first user, although I have to note there's no strong ordering in Gun. By default, you have to construct that yourself. So path into the first user and then access their where location and give us that data, okay? So that's just a quick showcase of the chaining API of Gun and how you can access deeply nested data by traversing through a table of users into the document of the user into a specific subset of that document, which is the data. And the performance metrics that we're going to measure is just how quickly in memory Gun can wind up reading these values out. So we're going to take that variable val, and we're just going to call the val callback, which gives you the data back. And we're going to then also test the longer format versus the shorter format. People are familiar with jQuery. It's always faster and more performant to cache the jQuery chain and reuse that versus reconstructing the chain every time. So let's jump over to the test, which if you wind up cloning Gun, it should just be in test/stool.html. So let me refresh. You can see the stats are actually already pretty good, 30 million ops a second and almost 7 million ops a second. But let's run that live because they jitter a little bit with the performance testing because it's using benchmark JS underneath. So that time was about a little bit less than 29 million ops. And the other one is about 6.5 million ops. So how are we getting this speed? It's if you saw that just running one function in JavaScript was only in Chrome, the current version of Chrome, was only 50 million ops a second. How are we getting that close to that much performance when we have to do all this data stuff? And the goal is tons and tons of caching, which we're going to jump into. I wanted to point out one extra thing, but I forget it. So let's just dive into the code now. So the first thing we want to look at is gun.get. How does get work? And that is right here. Gun.chain.get is equal to this function. Okay. So something that you're going to learn very, very quickly, that if you use named functions, you don't have the scope that typically your anonymous functions have access to. And that means you have to figure out a clever way of passing scope around. You'll see this in a moment. But first, we're going to say, hey, let's grab the prototype context of the chain. And get creates a new context of that chain. So we have the previous chain and we have this new chain that we're working on. Then we're going to grab a global variable in the database instance itself, which just provides quick lookup to metadata on certain data. And we got a temp variable. That's what I was going to show. Before jumping in, I actually want to show you that this is actually doing something. Console.logging kills your performance. So let me just really quickly show you. If I jump up here and uncomment the console.log, you'll actually see that the data, and the performance is going to be terrible because of the console.log, but you'll actually see that we are getting the data. Okay, so I just want to clarify, it is actually doing work. And then of course, I'm going to go back to commenting so I can test the true speed, and that should go back up to the 25 ops a second. Okay, that's what I wanted to indicate, that it's not just black magic and something is actually happening. All right, so back to the code. The goal though is that we get it to the point that we're hardly doing any work at all, okay? So first we have to validate the inputs to the get function. And the primary one is just what we're calling a lexical cursor. Realistically, for this example, I'm just going to jump down and show you that the lexical cursor is the key that we're trying to load. So it's just the universally unique identifier that we're doing pretty much an O1 lookup on, okay? But they can get a little bit more complicated, but we're not going to focus on that. So the first thing to do is to check to see if the parameter that we've received is indeed a string, because a couple things here. Typically, I would wind up using a library, and actually Gun comes with a type checking functions. But remember how calling a function itself costs a lot of performance. So I oftentimes just do gun.text.is lex, but that has a performance cost to it. So hopefully when things like Chrome actually inline small functions, I'll be able to go back to that because the performance cost will be negligible. But since we are worried about having it be the fastest in the current version of Chrome, as well as other browsers, we wind up doing this inline. So we check to see if it's a string. The second piece, besides that caching, right, is that you get a lot of performance gains if you put your primary code path as the very first if statement. Because if your primary code path is that first if statement, it doesn't have to evaluate any other if statements. However, if your primary code path is one of the last if statements, it has to do all of the other evaluations of comparisons before it, which slows things down just a little bit. Well, it's noticeable if you actually run the PTSD tests. And the reason why it's called PTSD, like I said, is because we're really trying to push the computer to its max, and that probably causes trauma to your poor little machine. So this is the case we're going to be dealing with. We're not going to be dealing with any of these other cases. So the next thing is we want to check if we already have the context, the chain context for this data in memory, okay? And we do that by using by, which just stores the metadata, and we pass it the key. And if that winds up returning successful, we can just skip this work all the way down to here, okay? Where we check to see if they also gave us a callback. And in this particular example here, we do not provide a callback. So we get to skip this work here and then just return gun. So if we have the chain, if the chain has already been used before, we can do an O1 lookup in memory that's really fast and literally do like nothing else. And that's how this first piece of the code winds up being really fast. But you're probably wondering, it's a database that actually has to get the data from somewhere. So the first time we do the lookup, it's going to be a cache miss. What is the work that's actually involved? So good thing you asked, or I rhetorically asked for you. If we do not happen to have the chain context already cached, we wind up having to perform that op ourselves. So I have a little utility function here called cache. I pass it by, lex, and back, and that function is right here. So again, rather than it being an anonymous, well, in this case, you wouldn't be using an anonymous function anyways, so I'll save that for later. We have to do a little bit more work. We say that, hey, we need to create a new chain context. And we do that by just calling back.chain, which creates a new context. We're not going to be exploring that code. It just creates a new self-contained context. We assign that into the metadata lookup, so that way we can get fast lookups forever afterwards. And we also assign that to the local variable, which we wind up returning, which gets returned back to the actual gun. And then the same thing resumes with checking to see if there's a callback and then returning gun. However, in order for us to then look up this data, and the data gets looked up across many different peers. Gun is fully peer-to-peer, fully decentralized. So what that means is it's going to look up data in the local storage in the browser. It's going to then make a request out to a server and look up the data on the server. If there's multiple servers, it's going to look the data up on multiple different servers. If there's other browser peers that are connected to you, it's going to look up the data on those browser peers because it's fully peer-to-peer. So we need a way to issue a request out to these peers. So we have what we're calling the lexical cursor, and the lexical cursor is a universal unique ID, which we call a SOL. And the only reason why we distinguish against a universal unique identifier is because a SOL is kind of like the head of a git commit. It's always the most recent version, well, most recent relative to your machine version of the data. It's not the hash. It's not your data previously. So UUID could potentially be represented as a hash of data at a particular point in time, but we always want to have the most access to the most recent. So we're just calling that SOL for kicks and giggles. It's a SOL of your data. Wahahaha. So we attach ID to the lexical cursor that we're going to wind up sending out. And then this code's not necessary because, like I said, it's the bleeding edge. So there's lots of things that are getting moved around as we work out performance. Then I do this really weird thing where I assign a function up here to this at thing. Now that's bizarre. And the reason why we have to do this is because, like I said, in order for us to get performance maximization, we don't want to have anonymous functions. And that means we have to name the function outside, but when we have it on the outside, we don't have scope. So the way that we've found to get scope is we attach that function to a local object that does have scope. And you can think of that local object as like an environment or in a context. It just has a bunch of data on it for this particular chain. So that way, when this function actually gets called, right, the scope is this context, okay? All right, so we're not there yet. So what we need to jump down, though, is back to, we get gun from the cache, and then if there's a callback, we do it, and else like return gun. So the weird thing here, though, is because there is no callback, we're not actually getting the data yet. But somehow the data does get resolved. That's because we're trying to do something else. We're trying to do lazy evaluation. And I'm just going to really quickly check to make sure that we're still streaming. We're still good?
Yeah.
Good. Okay. So it would be really, really terrible if you said get users and you had like 1 million users and Gun tried to start streaming 1 million users from the server down into your client. That would just not be happy. So we, in this new version, as we've been focusing on performance, do lazy evaluation such that we see that there's a path that's going to happen afterwards. And so we know that we have a very specific criterion with inside the users. And so we can actually take what would have been a scan over an entire table to just be O1 again, because it just says, hey, look up the users object and then look up this one property and return it to me, or where the property on that is 1. It might as well just be like Bob or their user ID, but just using 1. Okay, so how does that actually happen? Well, we need to then, yes.
One question. Can you go back to the code?
Yes.
Okay, so you had on the chain you called the function where, right? What? Path.
This. Okay.
What are the options that can be passed to the path function? And if there are multiple attributes?
So right now we don't support multiple attributes because we're designing with this idea of emergence and kind of reduce everything down to Occam's razor, the simplest pieces. And then what we can do is we're actually able to build other query languages on top of this underlying structure of lexical cursors. We will be able to build things like SQL on top of this. We'll be able to build MongoDB's queries back on top, but we haven't done that yet. So right now, the core version of Gun is just very, very simple in what it's doing. And so there's not a ton of configuration options. But the idea with Gun is that we're taking a very Unix or Node.js philosophy. We want most behavior to be implemented in user land that is specifically customized to real world application needs. And so we're trying to keep everything modular and as emergent as possible. As a result, I realistically think that as Gun becomes more and more popular, people are not going to be using Gun directly, but a lot of customized databases that are kind of wrap Gun that add these additional behaviors like SQL support. So right now, Path doesn't have very many options.
Okay.
So this chain of path isn't saying, hey, get the where property and the first property or the one property on users. It's saying path into that first user, let's just say Bob, and then inside of Bob, path into their property of where. So it's more of a document traversal, where your starting node in the graph is the users list or the users set or the users table or users collection, whatever you want to call it. We then navigate after that point from the table into a document style, which I think is pretty cool because you don't get that in a lot of other databases. All right, so where are we at? So now we want to jump down to path, okay? Chain.path. You might be wondering why I don't have these things all split up into separate files. I love splitting things up into separate files, but I'm one of those people that, and it's probably gonna get me a lot of hate. I don't really like Webpack and Gulp and Grunt, so I wind up bundling things myself and then running through the minify step manually. Just because I like to do a lot of testing and I don't want to worry about the compile steps, even if they're automated. But that's just a personal opinion, and please don't hate me for it. Okay, so back to this. The path function, the path method on the chain, is doing something similar as the get. We have the previous context, and we're going to have this new context. But I wind up wanting to do lazy evaluation, so I'm going to wind up grabbing the context from that previous thing, which is going to have the lexical cursor on it, because then we're going to add more information to the lexical cursor and only perform a request on that versus on both independently. So I'm just caching some variables here because there's benefit. So rather than like all over the place retyping this all the time, you have to do like 2 lookups. If you cache it, it's just 1 lookup, and that just gives you a small performance gain. The next thing I need to do is I'm actually going path going to kind of add its own metadata to the context, and that it does that by kind of attaching a path property to the metadata of the chain, and you'll see why we wind up using this. It's more for some complicated chain procedures we're not going to really dive into, but we'll get there. So first off, I want to validate that what we have sent into the function is what we're expecting. So I first say, if not field, however, because JavaScript is loose in types, it winds up thinking that, oh, 0 is that case. So we just protect against that. But if you pass in null or undefined, we basically want to treat that as like not something that is actually a field on a node. So realistically, I actually, to do, need to add error handle for this. But like I said, we're on the bleeding edge. So there's pieces that are missing and pieces are going to be changing around. So now if our validation is fine, I want to coerce the string into, whatever it is, into a string, in case it's a number, because I don't want to have to worry about checking for this ever again. There's a bunch of different ways you can coerce something into a string, and when I just did some jsperf.com checks, which unfortunately is down right now, this was the fastest, so I went with it.
I was always wondering what is the fastest method to get a string.
This is where micro optimizations can get you, because like I said, Chrome is doubling its performance speed currently in Chrome Canary. So for instance, I was getting 30 million, well, I should say above 25 million ops right here. And in the latest Chrome Canary, right here, in the latest Chrome Canary, we're getting so this is a MacBook Air, and we tested it on a MacBook Pro, so still commodity hardware. We're getting 80 million reads per second. And of course, there's no cache miss that's happening, but benchmarks are they're somewhat of a joke because they're always very optimistic and idealistic, but a lot of other people measure with these types of benchmarks, so it's just going along. And then we're actually creating an entire suite of tests for various real-world use cases. But I'm not going to go into that because that's an entire other topic on distributed testing, which we're also building a library to test Gun in distributed environments to formally verify, well, almost formally verify that the system works, even when there's network partitions and stuff like that. But again, that's going more into the theoretical stuff, and I'm showing code. And then the other cool stat is I ran this on my Android phone in the browser. So we're talking about low-end device, Android in the browser, and I was getting 5 million ops a second. And even this one, which is a kind of more of the deep query, was getting 1 million ops a second on an Android phone. We're really proud of this work that we've been working on, and we're excited to see where it goes. So back to the path function. What I'm going to wind up doing is like I did before. Because we have a document structure, that means potentially every new field. This is graphy stuff. So because you can, every node is stored independently, which allows you to look up that node directly and immediately without having to traverse a graph at all, or without having to traverse into a document. You can index anything anywhere. So as a result, when you're dealing with document-based queries, like we are with this path, let me check my time because I'm already expanding way too much information, but I'm going to keep on rolling with it. Every node that you start with and then you if you traverse it as a document from that point outwards, is going to have a slightly different view in the world than if you were to get to the exact same node if you were to traverse it as a document from another point of view of your data. So as a result, the reason why we're creating this path context here per the chain is because the chain is how you are traversing your data. And I then wind up needing to cache for each one of those chains the fields that you're traversing. So it's kind of what we were doing back up right here in Git, where we had that cache function and we're doing O1 lookup on the ID. It's basically the same thing, except for that's always global because it's the key or the ID for the system. While when it's with the path, it's relative to the ID. So we check to see if it already exists. And hey, guess what? If it already exists, we skip all of this work and immediately jump down to these two if statements and return gun. And this is actually, this is no longer needed because this is the latest commit and I broke some things in a more recent local version. I didn't commit because I want to not screw things up for the podcast. So I'm just going to ignore that stuff. Quick tip, this was both in the Git function, the Git method, as well as the path method, because you're always allowed to pass a Node.js style callback method. And so I checked for that here. I was originally just doing CB instance of function, but that was significantly slower because I think the max that Chrome could run with that was like 80 million ops a second. So actually, let's just test that really quickly because I bet people will get out of this. There's a function right there. F1 instance of function. There's a couple different ways you can check for a function, like type of, yeah, 80 million. And this one I found was the fastest a while ago, and then like a week later, it was slower than the other one. So like, again, be careful, micro optimizations because it can change with every new, with different browsers and every new release. So that's sad. Checking to see if something, type checking is 80 million ops a second. That's pathetic. So pro tip, I can just do CB and CB instance, because if we didn't even pass the callback in, like we didn't right here, then guess what? That right there is a lot faster to remove that edge case. But if it is true, it's going to be a little bit slower. But we go to a little bit extra work for the edge cases, and we try and optimize the hot paths of the code. So that pretty much gets skipped too. However, Mark, we haven't cached any of this data yet. In fact, we're supposed to be doing lazy evaluation. So what's going on? Well, okay, so back to this if statement. There is not a ref or a context or a chain that's already cached for this. So we actually have to do some work. But you see how we wind up doing this work once and we cache everything and we can get some really sweet performance gains. Now, there's a few things here. There's a joke that states that the two hardest things in computer science is naming things and cache validation. And then there's the aside of off by one errors. So it's true, cache validation when you're dealing with concurrency is very difficult. All of Gun is built around concurrency and conflict resolution. So we already have that across machines and down. I really want to show you demos of how it works, but I don't have time for that. So go watch some of the other videos. But in a single thread like JavaScript, you don't really have to worry about it too much, because as long as you maintain a reference you can always look up and then update, you can, just by using regular JavaScript objects, because it's passed by reference, you are doing cache and validation, updating to the latest thing. So there's not too much of a concern here, because we will incrementally update it as it happens. So we get to do it once, the hard work, and then just reuse that constantly updated cache throughout the rest of the process, which gives us performance gains. So since it doesn't exist, we want to create it. So we create a new chain context off of the previous chain. So this creates a new context that's safe for us to have our own environment to pass around. And we then, of course, assign that into something that we can then reuse later. Now, this is a little interesting. Because I'm trying to do lazy evaluation, I actually need to use the lexical cursor of the chain that's before me, because I need to use users. Users is the ID that we're looking up. We want to combine it with one. I don't want to mutate the chain before me, because if I ever reuse that, then I will have mutated it and it will return the wrong value. So what I wound up doing is just a quick shallow copy, which I have a little utility function for. I'll probably rename it to something else. That does a shallow copy of the previous chain's context, which has the lexical cursor on it, or aka the query that we're using. And that allows me to then take that thing. Well, first off, I need to assign the callback function that we have the context, so when this gets resolved. And I think in the recent code, I eliminated that as well to clean things up. As I'm going through, I'm trying to also simplify and make things more emergent. So sorry if a couple things are different with when I wind up pushing newer code in the future. Things are going to be different because it's the bleeding edge. So my current lexical context, I, of course, put my field on it. So a lex looks just something like this, right? We have the soul, which is users, and we want to add a particular key or a path or a field. Actually, I'm not going to say key because I'm going to reserve key for a key value lookup. I'm going to always say field. So when we're looking for a particular field on user, we're looking for, in this case, 1. Okay. The lexical cursor can be expanded with other things, but that's just what we're focusing on right now. So I need to make sure that I attach the field that the user wants onto my lexical cursor, and then I check to see if the previous context, the previous chain, happens to have a soul on it, because there isn't always a soul in the previous context. It might not have resolved yet. So we're just checking, or if the previous context. So let me show this in code with a test. Because we do 2 paths right after each other, that means when this path looks up its previous context, the lexical cursor is already going to have a UID on it and a field on it. So we can't do lazy evaluation on that because the cursor or the query is already filled out. We have to resolve it first before we can do the work that we want to do. So as long as the previous chain doesn't already have a field, and if there is a soul on that previous field, let's go ahead and add that soul to our lexical cursor. And then we do the magic trick of calling this event emitter. And I would love to go into the event emitter inside a gun because it's really, really cool. But I'm realistically not going to have time to do that. Maybe I can get to it later. So this event emitter does quite a few neat things. It works for asynchronous behavior, it works for synchronous behavior, and it also works for caching and memorizing things. It also allows you, so I'm just going to high level explain rather than diving into the code. It also allows you to take a series of events and you can like pause them at one of the listeners. So that way you can do some asynchronous work and then resume. So people who love ES6 and ES7 yields and generators and stuff like that, it kind of gives you that behavior in ES5. And again, don't hate on me for loving ES5. You'll be horrified. I actually test my code all the way back to IE6. But don't hate on me too much. By the way, Gun is not, you think if I test all the way back to IE6, Gun must have a bunch of bloatware. It doesn't. The current stable release of Gun is less than 10 kilobytes. So it's like 9 kilobytes or something like that. So it's very, very small, but it does a lot. All right, so this event emitter, let's jump to where on happens. So I'm going to go to .on. And I have this ability to extend the event emitter with gun-specific behavior. So when I wind up in .path calling this event right here, it's going to say, hey, if we already have a memorized item on that event, we can just immediately apply that event directly. However, if we don't have any data memorized, then we actually need to perform the request that goes out and gets the data. Okay, does that make sense? So that's what we're now going to dive into, where we're actually performing a GET request. And that's done with G gun.get, and we pass it the context. All right. So There's two options with gun.git. There is a slower, more friendly user API where you can pass in your cursor and your callbacks. That way it can be anonymous and you get the result. Or there's the nice fast version right here, which checks to see if you've already formatted everything into a context and just runs with it and skips all this work of validation. Don't use the fast version unless you know what you're doing. So if you want to help extend and create modules to Gun, do that. All right, so now it turns out that the way that we load data from peers is just another event stream. So a lot of this is just a streaming architecture. We emit globally on Gun now, rather than on a chain specific, a GET request, and we pass it a context. So now let's look in the code how many different things listen to a GET event. Well, there's one right nearby, and this happens to be the in-memory one. So I'm not really going to explore it other than the fact that if the thing that we're requesting is already in memory, just immediately call it callback with Node.js error data style. And then, as I told you earlier, I want to actually done for this propagation.
Hey, Mark. Sorry, but I cannot hear you very well.
Okay.
Okay.
Tapping 1, 2, 3. Yes, go for it. Please interrupt me.
Okay. Do you have any policy on in-memory data expiry? Because you fetch some data from a server, you cache it, but the data might change.
Yeah, great question. Great question. So this is a really cool thing about Gun is that since everything's real time, the in-memory cache gets live updated as new data gets updated. It gets the server. Well, so technically there isn't really even a Gun server. The Gun server is just a Node.js Gun peer, but because WebRTC kind of sucks and you have to have a signaling server and stuff like that, it's just easier to run a server which does WebSocket replication for you. But Gun would work on a WebRTC setup. We just haven't focused on it because WebRTC itself is so it has some nuisances to it, but we're working on it. So what that means is we're connected to the server, and the server is actually live pushing any of the concurrent updates out to us. So that way we then update our in-memory cache. So we actually perform a GET request only once, and then everything else is just listeners that stream the data in. So think observables and stuff like that. Of course, it gets a little tricky because what happens if the network disconnects? It's also okay. Because of Gun's peer-to-peer architecture, it's called a master database. And that actually means everywhere that the data exists, whether that's in memory in the browser, in local storage in the browser, on the server in memory, on the server in disk, on the server in S3, or in other peers, every copy of the data is considered a legitimate copy of the data. And then the magic of Gun is as all these different out-of-sync versions of the data, the deltas, get pushed to each other, it resolves all the conflict using a deterministic algorithm such that every peer eventually consistent, repeating that a lot because you don't want to use Gun for like banking and accounting and finances where things are strongly inconsistent. Eventually consistent, all peers resolve to the exact same data within that quote view of state. But that's entirely another discussion. So a lot of that cache invalidation is being handled. And we're going to dive into it a little bit, but you're actually going to see the algorithm for it if we wind up having time. I'm probably going way too slow. How is my pacing so far?
It's okay. Take your time. We can, if there are more things to present, we can do another episode. But
okay.
So it's very interesting.
You are liking the line by line?
Yeah.
Good. Okay. All right. So great question. That winds up getting resolved because we do a GET request once, and then any new updates to the data get pushed to the peers. And then the peers, when they get the data pushed themselves, resolve and merge that data into your local copy. So that is how we deal with cache invalidation. Well, that's the shortened version. So if it happens to be in memory, just always return in memory one. And as long as, like I said, data is going to push to us, that in memory one will always be the most recent up to date. And if we're offline, we can still operate on it. Yeah, we're not going to go to that. So if it is in memory, if we do have it in memory, we don't actually have to make requests out to local storage or requests out to other peers or to the server. So we call event.stun, which prevents the other listeners from receiving it. So that way they don't do any work. But we don't have a cache. So the point was to skip over that. So let's look for another listener for Git, and aha. Now, this is where I'm probably being really bad. This is technically the browser module, and it definitely should be its own file. But like I said, because I hate compile steps, I want to just have it by default bundled into Gun. So I don't actually count this code right here as being Gun core. So don't judge me for my coding style. Everybody has different styles, and I respect that. So I do hope that you guys really like the very streaming event emitter architecture, because it makes everything super modular. Okay, so I have a wrapper around local storage called tab.store.git, and I wind up taking the lexical cursor from our at context, and I wind up, there's an option to just prefix your local storage, that way it doesn't conflict with other things, and then do a lookup for the soul. And then I pass the actual callback function, which is this guy. And all that does is actually returns the data from local storage. It's just a thin wrapper around it. But here's an interesting thing. If the data exists, I then call the callback at.cb error data. But because I don't really trust local storage very much, if it doesn't happen to have any of the data, I actually don't have it call back anything. Technically, you're supposed to call back the system with like, oh, we couldn't find the data, which is a separate event from saying, oh, an error happened, which is a separate event from data existed. But I don't really trust local storage. And because peer-to-peer algorithms get a little wonky, you never know whether the data exists or not. So just because a peer says that they don't have the data doesn't mean that the data doesn't actually exist. But if you wind up wanting to write to that data, then Gun has to create a new ID for that data. And if it winds up creating a new ID every single time it can't find it from its local caching value, it just creates a bunch of IDs that wind up having to be aggregated into the actual key that you're looking it up. And that's just extra work, which isn't necessary. So long story short, I'm not going to dive into that too much. I don't have local storage actually return if it can't find the data, because I want to leave it to, and this is starting to where assumptions start coming in. Gun itself doesn't have any assumptions, but this driver here, which should be considered as separate from Gun, does have assumptions. The assumption is, oh, I really want to make sure I check against a server or another peer before I say that the data can't be found. So hopefully that made sense, but if it doesn't, we can do other discussions on the philosophical nature of distributed systems. All right, so that didn't work. So that means this listener, the local storage listener for the GET request, didn't wind up doing anything. So now let's go to the next listener for request. And in this case, it is our WebSocket implementation, which is also another driver. It has to do a little bit more work, and I'm not going to go into that because I'm going to jump back to this. When we wound up writing the data, we already wrote it in memory. So actually, we already have it in memory, so we can just reply immediately. So I wanted to show you the architecture of how easy it is to add a bunch of plugins that pull data from other sources. It's really easy. But at the end of the day, it has to wind up calling at.cb error data. So now let's jump back to gun.git, because whether it's in memory or from local storage or from another peer, the data is going to get returned to us. So this event listener, the callback, is actually this thing right here. Because as you see, on the at context, I assign got to CB. And the beautiful thing here is, well, actually, I don't wind up using it here because I wind up just calling another event system, is the current context is just this context because of how I assigned it right there. So I don't have to worry about creating anonymous functions, which saves performance. All right, so the first thing it does is if there was an error, it just, for development, it just automatically logs that, so it's easier to debug what's going on. Elsewise, this is really cool. As soon as data is getting streamed into Gun, we actually have a modular system that allows us to do transformations on those streams of data. So as a result, I need to call all of those stream listeners. And I do that, but I wind up wanting to create a copy of the context with the new local variables, because if one of the GET hooks that's actually pulling data from other sources or from disk happens to reply, if we get multiple responses, we can't mutate the current context because then you get race conditions. So we actually have to copy the current context with this local scope of the data that we've received back. And that goes into the stream function. Woohoo! Okay. So the first stream function just winds up doing the important work of merging the data that we've received into the in-memory cache. And this actually does the conflict resolution. So this is a point where, help me out here. Do you want me to actually jump into this algorithm that shows how the conflict resolution happens? Or should I just stick to, you guys can look that up someplace else or do a separate talk on it, and we keep on going with the code flow here?
So I would like to see, but I would really like to continue with the flow.
Okay, cool.
Stopping to focus.
So
I really think that that's another topic, and I would
yeah.
really like to see it as a.
Oh, I'll skip this. Ham.node just normalizes some of the data and winds up iterating over each property in the node, which then passes it to the more important thing, which is this map function. And this map function for every field on every node in the graph winds up performing what's called the hypothetical amnesia machine, which is the name, the silly name I gave for the conflict resolution algorithm. And that is where the interesting stuff is. And that algorithm isn't that large. It's plenty commented. It's, I think, about 20 lines of code or less. And that's it. And the way it works is it treats, it does timestamp evaluation, but timestamps are dangerous because if another peer has clock drift, or if they set their clock to 2 years in the future, that can compromise the system. It's a security, well, I shouldn't say security, it's just an authorization vulnerability. So it does timestamp comparison, but to mitigate the timestamp vulnerabilities, it also does vector comparisons, where it treats the timestamp as a vector relative to the other updates that it's received. So that way it can do this intelligent thing where it, no, that's a separate talk. And then if there winds up being a conflict even on, so if there winds up being a conflict on the timestamp on the vector, then there's an even further thing that it reduces down to a lexical evaluation. Lexical sort sounds like a really, really naive way to get conflict resolution when buttons are pushed. Or when you hit the furthest edge cases. It's intentionally naive because what we're looking for is a deterministic algorithm that's guaranteed to work on every single machine in the entire universe. And lexical sort, I'm pretty sure, is going to be available on every single machine. The beauty of this is it's very, very low level, and you're actually able to build other types of resolutions on top of the system using fancy data structures like CRDTs, conflict-free replicated data types, or also convergent replicated data types, or directed acyclical graphs, which is what Git uses, which is it's just a tree. It's just a linked list, pretty much. So there's all sorts of things you can build on top of this to get more fine-tuned things, and that's where I was saying earlier, a lot of people are probably going to be using a database that wraps around Gun that has those specific business-specific logic already baked into them. So CRDTs and stuff like that. Anyways, that's the base level one that we're able to build everything else off of. It's very, very emergent. So jumping back. Emergence is the most important thing for us in Gun, is to build a system that's capable of creating even more complex behavior on top of it. Unix, Node.js philosophy. All right, we were in stream, right? So the first stream function does the conflict resolution transformation to the data. And that winds up being the most important piece because that's what all of Gun is built around. Well, I should say Gun is built around the conflict resolution algorithm and this concept of graph data structures, which we went over at the beginning. If there doesn't happen to be any data that it was merging into, then that sounds like the data was formatted incorrectly, so we throw an error and stun the event. So now the next thing, we're going to jump to this stream. And this stream also, I'm not going to dive into detail, but you'll recognize it's got the by in there. the meta or the by, it's this right here is just a stream that quickly adds this data into that cached reference and updates it. So that way, when we reuse it again, it's just got the latest values. So that's also not super important. That's very specific to the local machine. This next one is really, really cool because it's a little bit mind-boggling. This function right here, you can think of it as being more of a server-side function. So even though we're like in the browser and in JavaScript, Gun actually runs everywhere. It's isomorphic or universal. So both the server and the client, because they're not actually server-client, they're just peer-peers, both of the peers do the same query filter on the lexical cursor. So think about this as being the server that has received that lexical cursor. We wind up saying that, hey, we want to make sure that the lexical, actually I have the lexical cursor right here, that the data that we're returning to the user has this ID of users, and that it is limited to just this one field of the field 1, okay? So it first does a check against the ID, okay, to make sure that that's the only thing that winds up getting returned down to the client. But then it also does a check on the field property. And if you happen to have this users list that has millions of users, it just creates a copy of the node with just the one property on it. And this code is pretty ugly here, but it gets the job done. It just it removes all the other pieces for the data that's getting responded. So now the server is only replying with the exact subset of the data that you want, so you don't have to waste bandwidth. But then the nice thing is then the same function winds up getting run on the client again. So the client winds up doing the exact same query in case the server didn't have that fancy query logic on. If the server did return 1 million users, I don't know why, just because let's say somebody didn't implement a query function on the server, the client would also do the appropriate query filter and return only the data that you were requesting. But of course, then you have wasted bandwidth. But the point is you still get the data that you wind up wanting. All right, so that winds up being really cool. Now the next stream function is we're done. Yes?
Another question. It seems to me that it's really important to have the same version of plugins running on the server on the browser. Is that true?
I'd say the same version of Gun is critically important. Same version as the plugins, not necessarily, because you might want to do some custom fancy stuff on the server because you know your server is more beefy than a little browser. And then on the browser, you might want to have a different set of plugins that like adapt into React or Angular or something like that, or do other types of data transformations. So yes, generally speaking, to keep your system more deterministic and easier to reason about, you want to have every peer running the same algorithms, but that doesn't mean that, so okay, maybe I should back up. The cool thing with peer-to-peer systems is they're emergent. You can build federated systems like email on top of, let's say, like BitTorrent. You could build email on top of BitTorrent. You could also build centralized systems on top of federated systems, on top of decentralized systems or peer-to-peer systems. So if you wind up having a traditional SaaS app where you want to have a master server infrastructure but not have to worry about all the DevOps, you just run Gun as a cluster on your infrastructure and it does all that magic. But then when your clients are connecting to it, you have different logic because you actually want to do security and authentication and authorization. So in this case, the server might have an authorization plug into the stream, do authorization and reject and intentionally reject syncing with a client that's not valid. Does that make sense?
Yeah.
But generally speaking, I do think it's helpful to make sure that your system is purely deterministic, and so the same code's running everywhere. And yeah, it is important to make sure the same version of Gun, especially because as we're moving to production-ready release, we're changing the API a little bit. But hopefully that production-ready release is coming up soon with the crazy performance stuff we've been working on. Okay, so that is into the streams that I've like just by default built in. So once that is done, the event emitter actually has this callback once all the streams are done, or in the case that if the stream gets stunned, it just resumes execution here. And that function is right here. Woohoo! And that receives a new context, and actually this isn't necessary anymore. it then calls that original callback all the way back when we, with @array and @node that we had set up when we triggered the event listener, which said we don't have a memorized result, so we need to actually go call gun, which was all the way back in .path, where we were down here and we were saving data to this. Okay, so now we've rewound back up the stack. As you see, the get function, the function that's getting called, the callback here, but we're caching it so we get performance improvements, is this one right here. And this is changing up a little bit more in the newer stuff I'm working on to make it a little bit more emergent, but let's just roll with this because it's the same idea. So this is, let's just scroll up, cached right here. Okay, it's cached right here. And that winds up just calling fields.call this. Why am I doing that? Well, because annoyingly, Node.js callback style of error node doesn't really allow me to pass context very well unless I attach it to the reply data, but then that kind of gets the developer's API a little messy. So I'm just doing, unfortunately, an extra function call, but since this gets cached at the end of the day, it winds up not getting called. I'm gonna do an extra function call to transform this thing back into our environment variable context that allow us to have access to all of the scoped variables versus the one. And fields is right down here. And what fields does is it's important because the path command can traverse into multiple different fields, okay? If there happen to be multiple different fields. So what we want to do is we want to actually, well, okay, I'll get there in a moment. First off, I'm going to skip over this data a little bit. Well, let me go back over here. So let's say we had done a query for mark.friend. The value that I'm going to get back is just a pointer to another sol. And I don't really want to return that to the user because the user actually wants the data, not the pointer. So what I'm doing here in the path command is I'm checking to see if the previous field that is on the node we've received happens to be a relation. And if it is a relation, to go ahead and call gun.get again, where the lexical cursor is just the sol. And this extra field here is in case we wind up having a double path, where if we grabbed all of Bob at this point and we were just going to wind up doing a lookup on the single property of where, it's the same thing as if we were to grab all users. So we actually also want to make sure that when we do this subsequent lookup to resolve that link, if there happens to be another path after it, that we do lazy evaluation on that as well. But generally speaking, most of the time, it's just going to be another lookup on a direct sol,
Okay,
which runs.
I want to clarify one thing. You at one point you said that you query for mark.friend.
Well, I was just giving that as an example. So an actual example we're going over, it's this query. And I was just showing an example that because of the way that the data is structured, if I do a query for asdf.friend, what I get back from the server is just a pointer. And I don't want to return the pointer to the end developer. I want to return the actual friend. I want to return this. So that means I have to do a subsequent lookup to resolve it. But the nice thing is it's still all O1, but it's just each step is O1. So it winds up being O in, where in is the length of your path. Does that make sense?
Yeah.
But once it's done all of those, it winds up being in memory and cache anyways. Okay, so the query we're actually doing is not this. And I hate using the word query because part of the philosophy of Gun is to actually get rid of queries and instead actually treat everything as O1 lookups. And that's what lexical cursors technically are. But I won't go on that rant here. Okay, 2:57. We're almost at an hour. But I think we're almost done with this stretch at least. So go ahead and resolve that extra lookup if it needs to be done, but recursively call ourselves back into this fields function. So then once we actually have the data that we want, which is, let's say, Bob here that has a bunch of different properties on him, one of which includes where, we want to iterate over all the properties on the node. And that's also cached, but all it does is return us the value and the field on on that node. And then I wind up wanting to call a new event listener for path field. And the reason why this is important is because back down here in the actual method, the actual method call, right? We wind up listening to, we wind up listening to updates on this very specific results. And the reason why this is important is because in our previous version of Gun, well, not the immediate previous version, is I was attaching listeners to the node as a whole. But if you wound up having like a million users, a million methods would attach their callback listeners onto any update to the node, because I would wind up just filtering. Like I'd just check, oh, what is my context? I'd get an update on this node, check my context, see that I actually have this particular path, check to see if it's in this node, and then return. But the issue, as we established earlier, every function call is really expensive. So if I wind up having this constantly growing list of event listeners on the node itself, then the performance gets that much slower every single time. So if we instead say, let's create an event listener for each specific field, then what that means is we're able to reuse that event listener, and we're also able to say, we're also only subscribing to changes that are absolutely necessary for what we're listening to, so performance is faster. Okay, now this all boils down to the important thing of link, which I think I might have already gone over. The link code here is actually really messy and it's been cleaned up a bunch, but let's just say that the moral of this, other than handling edge cases like the data doesn't exist or if there's an error, is to just call the next chain, okay? Because, and the reason why I'm saying I'm gonna skip all that stuff is because we don't have a callback right here. Our callback is actually over here, which is the next piece of the chain. So I'm just gonna focus on saying, hey, we're gonna call that next chain. All right, so now we need to look at what the next chain is, in.val. And in.val doesn't do much at all. It just says, hey, first off, is the value already cached? Then call the callback immediately. Don't waste doing any work. However, if it also has to do lazy evaluation, it runs through the same process where it copies the context, calls the event listener, which then triggers the real get request. And then when that resolves, it winds up just attaching the return data to this cached, to the context of the data. So that way, when we rerun it, all we're doing is hitting this at.val and then calling the callback immediately. And there you go, we are done. So we went through all the hard work that happens once. And then I'm gonna finish with rerunning the test and showing what's happening. So we get users, let's assume it's already cached, and we path into one, and we path into where, and we do okay. So the actual code that winds up being run after we do the work once is the Lex is a string. We have that cached. Skip all this work. Don't do that, return gun, okay? So we've hardly done any work. Now, go to in.path. Get our previous context. Make sure the field's validated. Coerce the field, look it up. If it's already cached, skip all that work, return the next thing. Now, the next thing again is path again. So we wind up just performing the same operation again. And then the last step is to go to val. As, hey, the data is already cached for this context. Oh, just by the way, val does not create a new context because it's not mutating the data anyway. It's just reading your value out. So it doesn't have to create a new context. It's already cached. Now call the callback function. So literally, when we wind up all the hard work up front and then running it again and again, everything that we're doing is basically do a string comparison, O1 lookup to a cache reference, return. That's the end of one function call. Next function call, do a lookup for that context. Skip, coerce the field, and then do a lookup, and then skip all the work and return. So it's basically if statement, function call, if statement. And so to do one function call, two function call, three function call, four function call, five function call, the actual calling the OK, with a couple if statements, That is everything that's happening, and we're able to get about 1 million ops a second on an Android phone in the browser, or on this machine, a MacBook Air, 6 million ops a second for this query. And most of that is just a limitation of JavaScript itself. So I hope this was useful. I hope you get excited about Gun. I hope I've brought up lots of interesting things that have perked your interest, everything from the modular architecture to the performance testing methodology to the quirks in like V8 and the Firefox and stuff like that. And you check us out. And I hope you've learned stuff by reading the source and checking out what's going on. Please jump in and help contribute. We would really appreciate that and welcome you into our community. So let's jump back to you.
So,
anything else?
well, if we have any live audience that would like to ask a question, we enable the Q&A section for the live hangout, or you can use the read the source hashtag on Twitter if you can ask a question, or you can ask the question later on the YouTube video. But I still have 2 questions. Probably
okay, awesome.
Relevant. So I noticed that you, in order to do a lot of micro optimizations, you did a lot of caching.
Yes.
So does this have any memory impact?
Well, it will absolutely have memory impact if all of your caching is spread out all over the place, okay? But as you saw, I was using that metadata of the graph called by, and I always wind up putting the cached and the updates to the cache back there. So I wind up having a central, despite the fact that it's peer-to-peer, on this particular peer, on this particular process, in this particular thread in JavaScript, I wind up centralizing all the cache to one area, which winds up not having as much duplication. And of course, there's some places you can't always get it centralized because, like I said, each perspective of the data has a slightly different document structure, so you wind up having to cache that. But if that's the data you're reusing and using, then you need to use it. And the goal, we haven't done this yet, is to have an LRU system, least recently used. So basically, if you can set a limit of how much memory you want to use, and if you exceed that memory, Gun will look for the least read item and just flush it. And flushing it should be easier with this new architecture because most of that data is centralized in the graph, in the memory, not in the database system as a whole, to that one pass by reference JavaScript graph thing meta. Does that make sense? So memory utilization, we haven't checked. Firefox has this really cool new tool in their developer, which Chrome doesn't have, and it just came out, I think, like 2 weeks ago, that actually allows you to check memory utilization, but we haven't done testing yet in that because we've been focusing on performance. Somebody tried to use our database to build to build a game, and we learned all sorts of performance things and realized we need to get our butt up to speed and make it so that Gun is capable of like being there to run the game state of your game, and then you get kind of multiplayer stuff kind of for free. You get it for free, but you still have to think about the causality of your game. So does that answer your question?
Yeah. And the second question, ever thought about using ES6 features, at least for the Node.js server implementation?
So 2 answers. The engineers that help build Gun, part of the team, they love ES6, they love Babel, they love Webpack and all that stuff. So they're opposite of me. They like all the tooling and all the new cool features. So I'm going to say that yes, in the team and in our ecosystem, there's lots of ES6 and Webpack stuff. My second point is that before I ever use any new ES6 feature, because I'm taking the PTSD development methodology, I'm going to check the performance of splats, the performance of things, because using arguments is terrible for your performance. So lots of these conveniences, like anonymous functions, using the arguments object, just tear performance apart. Now, this is the difference between a library developer and an app developer. As an app developer, you're not really worrying about performance. Like somebody clicks on something and it runs once. It's not like it's repeating that 1 million times. You're having to worry about frame rate and stuff like that. But since we're a library, somebody might use this in a game, and then we have to make sure we work there too. So I'm not trying to give people the impression that they should go into crazy micro-optimizations, that they should throw out anonymous functions, and that they should not use these conveniences. Go ahead and use that. If that makes you more productive, if that makes you happier, if that gets your code done faster, please do that, because everybody else is going to be happier. But I'm just going to be sitting back here saying, ooh, but what's the performance characteristics? And I haven't run them yet. But it's easy. You just go to the PTSD website, drop in some things, try running it, clone it, whatever. And I'm trying to get PTSD performance testing speed development as kind of the new TDD. So if you guys can like spread the word and like get it as this buzzword, that'd be great, because I think it's really fascinating. You learn so much about the black magic that's happening underneath the hood and the engine, and whether it is caching functions, whether it's not, and all that stuff. So did that answer your question? I go on these rants.
Okay, Mark, thank you very much. That was awesome.
Thank you.
I really got interested into micro optimization, so I just want to go back to my applications and do some micro optimization. So we are comment on our video is that
don't get really quickly, don't get lost too much in the micro optimizations. The point of PTSD is to give you a framework where you can just like toss these things in really quickly, test them immediately, so that way you don't get lost in a sea of like freaked out about micro optimizations. You just like throw it into these test beds, run them really quickly, and then go back to work. That's the point of the speed development with PTSD, while not sacrificing performance. So cool, but don't get lost too much. So now I'll shut up.
Okay, so we're waiting for comments on our video. Mark, we are going to get back to you if there are any questions. So thank you very much for accepting our invitation. That was awesome, and I would really like to see more of your work.
It's been an honor being on the show. Thanks so much.
Thank you. Thank you, everybody. See you next time.